Welcome to this lecture. Today we will discuss the choice of specific magnetic loading, that is B average, specific electric loading, that is AC, and the selection of number of poles in DC machines. First we will discuss the choice of specific magnetic loading, that is B average. The first factor to be considered is the flux density in teeth. If we use a high value of B average, that is the average air gap flux density, then the flux density in the armature teeth will also be high. Then the value of flux density at the root of the teeth should not exceed 2.2 Weber per meter square. That is a condition. The flux density at the root of the teeth should not exceed 2.2 Weber per meter square. Otherwise, it may lead to increased iron losses and higher ampere turns required, that is, higher MMF required for passing the flux through teeth. This leads to increased copper loss and cost of copper. So, that means a high value of flux density leads to higher iron losses, higher copper losses, and cost of copper. Then second factor is frequency. In the case of a DC machine, the frequency of flux reversals F is equal to capital N, that is speed in RPM into number of poles divided by 120, or speed in RPS small letter n into P by 2. So if we use a higher frequency, then it leads to increased iron losses in the armature core and teeth. So if we use a high value of B average, then the frequency of the machine should not be high. The third point is voltage rating of the machine. If the voltage rating of the machine is high, then the space required for insulation will be more. So for a given diameter, less space is available for iron, leading to narrower teeth. The teeth will be narrower. If the teeth becomes narrower, then the flux density in teeth becomes high, which cannot be allowed. That means for high voltage machines, we can't use a high value of B average. So the typical value of B average varies from 0.4 to 0.8 Weber per meter square. Next, we will discuss the choice of specific electric loading. The factors are, first one, temperature rise. As we know, the equation for AC is equal to ZIZ by pi d. So a higher value of AC results in higher temperature rise of machine because the current becomes high. So obviously the copper losses will be more, so the temperature will be increased. So the temperature rise depends on the method of cooling and type of enclosure. So we have to keep the temperature rise within the limit when we choose the value of AC. Next is the speed of machine. If the speed of the machine is high, that is, for high speed machines, the ventilation will be better, so we can use a high value of AC. Next point, voltage. For high voltage machines, they require a large space for insulation, so there is less space for conductors. So Z cannot be increased further if we are using a high voltage machine. So for high voltage machines, small value of AC should be used. Next point is size of machine. So in the case of a large machine, there is more space for accommodating copper conductors, so we can use a high value of AC. Next point is armature reaction. If the value of AC is high, then the armature MMF becomes high. This leads to reduction in main flux due to the effect of armature flux. That means greater distortion will be there in the field form. So we have to, in order to compensate this, we have to provide more MMF from the main field, that is from the field the number of turns in the field winding should be high. So the overall cost of copper in the machine will increase. The next point is commutation. As you know, AC is equal to ZIZ by pi d. The value of AC will be high if Z is high or if D is small. If the number of conductors is more or if the diameter is smaller, the value of AC will be high. Let's consider both the cases. First, let's see what is the reason for poor commutation. If there is a poor commutation, that means the value of reactance voltage is high. Okay, then if the value of number of conductors Z, if the value of Z is high, then the reactance voltage increases, which leads to poor commutation. Then if you are using a smaller diameter, then also the value of reactance voltage increases due to the use of deeper slots. This also leads to poor commutation. So a higher value of AC leads to poor commutation. The typical values of AC varies from 15,000 to 50,000 ampere conductors per meter. Next, we will discuss the selection of number of poles. So these are the factors to be considered while selecting the number of poles of a DC machine. First factor is frequency. As you know, the frequency of flux reversals F is equal to NP by 120. So if as the number of poles increases, then frequency also increases, which leads to higher core loss in the armature. So the efficiency of the machine decreases. Next point is weight of iron used for yoke. As the number of poles increases, the area of cross section of yoke, this is the area of cross section of yoke, and hence the weight of iron used for yoke reduces. Let's consider these two examples. In the first case, it is a two-pole machine. This is a two-pole machine and this is a four-pole machine. In this two-pole machine, the flux passing through the yoke is 5 by 4, where 5 is the total flux. If 5 is the total flux, flux through the yoke is 5 by 4. But in the case of a four-pole machine, the flux through yoke is 5 by 8. That means the thickness of yoke can be reduced if you increase the number of poles. Next is weight of iron used for armature core. For a given value of hysteresis loss, the area of armature core decreases with increase in number of poles. That means if you increase the number of poles, the area of armature core decreases. That means the weight of iron in armature core decreases as the number of poles increases. Next point is weight of copper. There is two aspects, weight of copper in armature conductors as well as the weight of copper in field conductors. Both are to be considered. So in the case of armature conductors, if you increase the number of poles, then the length of overhang decreases. Length of overhang decreases. That is the reason why the weight of copper used in armature conductors decreases if you increase the number of poles. Similarly, the weight of copper required for field conductors decreases with increase in number of poles. Next point is length of commutator. The length of commutator is determined by the size of brush or thickness of brush, and thickness of brush depends on the current, or thickness of brush depends on the current through the brush arm, and the current through brush arm IB is equal to 2 times current per parallel path. In the case of a lap wound machine, current per parallel path can be written as IA by P, where number of parallel paths is equal to number of poles in the case of lap wound machines. So current per brush arm is equal to 2 into IA by P. So if you increase the number of poles, then the current per brush arm becomes lesser, and we can assume that the thickness of brush will also reduce, which leads to reduction in the length of commutator and reduction in the overall length of the machine. Next is flashover. The number of brush arm is equal to the number of poles. So if you increase the number of poles, then the distance between adjacent brush arms decreases. So there is a possibility of flashover. So that is a disadvantage of higher number of poles. Next is labor charges. That's also a disadvantage. If you increase the number of poles, labor charge. So this is a consolidated points. These are the points which are to be remembered if you are asked to write the advantages of larger number of poles or disadvantages of larger number of poles. So first is advantages. Advantages means the reduction in weight of armature core and yoke, reduction in cost of armature and field conductors, reduction in overall length and diameter, reduction in length of commutator, reduction in distortion of field form under load conditions. And disadvantages of large number of poles is increase in frequency of flux reversals, increase in labor charges, and these are the guiding factors or guidelines for the selection of number of poles. So these are to be kept in mind when we design the number of poles and do the problems regarding the selection of number of poles. First one is the frequency of flux reversals F should lie between 25 Hz to 50 Hz. And next, the current per parallel path, that is IA by A, should be less than or equal to 200 ampere. Similarly, current per brush arm should be less than or equal to 400 ampere. This is the condition. And the third point, the armature MMF should not be too large. Armature MMF means ATA. ATA is equal to ZIZ by 2P. It should not be too large, and the range is 5000 to 12,500 ampere turns. Thank you.